Dear students, in the last video we studied the electric field due to the dipole. We calculated the axial electric field and equatorial electric field. In this video we are going to find out we are going to understand the continuous charge distribution. First of all, we are going to understand what is the distribution of charge, what is the continuous distribution of charge. If the charges are uniformly distributed, then we can say that they are continuously distributed charges. Here we are not going to discuss the discrete distribution of charges, right? So in that there are the three types of continuous charge distribution. First one is line charge distribution. See, line charge distribution means what? When the charges are distributed, uniformly distributed along a line, that is known as the line charge distribution. The charges are uniformly distributed along a line, that is known as the line charge distribution. Now the definition that we are going to study, that is line charge density. The line charge density denoted by letter lambda. See, line charge density denoted by letter lambda. What is the meaning of line charge density? It means total charge on the line divided by length of the line. Charge divided by line, that we can say, length of the line, that we can say. Total charge on line divided by length of that line, that is known as the lambda. Lambda is known as the line charge density. What is the SI unit of line charge density? See, SI unit of lambda, that is equal to charge per unit length. Means what is the SI unit of charge? That is coulomb, capital C, coulomb. And what is the SI unit of length? That is meter, right? Coulomb meter. Keep in mind, C must be capital. If you write C small, then it is readable as centimeter, right? So it will be wrong. So this is right, coulomb meter. Coulomb per meter. Length is on the downside. So that's why we write coulomb per meter. Okay. Now what is the dimension formula for this lambda? Dimensional formula for the lambda. So how we can calculate dimensional formula? What is the dimensional formula for charge? As we have solved it earlier in the previous video, that is a raised to 1 t raised to 1. So dimensional formula for the charge is a raised to 1 t raised to 1. What is the dimensional formula for length? That is L raised to 1. So what we can write? M raised to 0, L raised to minus 1, a raised to 1 and t raised to 1. It is the dimensional formula for lambda. Dimensional formula for lambda. See, this is the line charge distribution. There may be a MCQ. What is the SI unit of line charge? What is the SI unit of lambda? What is the dimensional formula for lambda? Right. The next thing that we are going to consider, and second type that we are going to discuss, surface charge distribution. After the line, we will discuss surface charge distribution. Second thing, that is surface charge distribution, right? See, in this, what we can see, that the charges are uniformly distributed on the surface. Suppose the charges are uniformly distributed on the wall, on the sheet, that we can see that surface charge distribution. Suppose we are having a balloon and on the skin of the balloon, if the charges are uniformly distributed, then we can say that it is the surface charge distribution. Now we are going to define surface charge density. See, surface charge density. See the symbol for that, surface charge density denoted by letter sigma. Right? Sigma is the symbol for surface charge density. The definition of sigma equal to what? Charge per unit area. So total charge divided by area. So total charge on area, right? Total charge on area divided by area, right? So this is the sigma, surface charge density. What is the SI unit? SI unit of sigma. See, what is the SI unit of charge? That is coulomb. What is the SI unit of area? That is meter square, right? Per meter square. So coulomb per meter square is the SI unit of sigma. Next, what is the dimensional formula for the sigma? That is, we will write. See, what is the dimensional formula for charge? That we know that A raised to 1, T raised to 1. And what is the dimension formula for area? That is L square. So we will write L square over here. So finally, M raised to 0, L raised to minus 2, A raised to 1 and T raised to 1. This is the dimensional formula for surface charge density. The third type that we are going to discuss, that is volume charge density, volume charge distribution. Third one, volume charge distribution. Charges are uniformly distributed inside the volume, that is known as the volume charge distribution. Now we will see the definition of volume charge density. See, volume charge density denoted by letter rho, right? What is the formula for that? Rho equal to total charge inside the volume divided by volume, capital V we can write. So charge by V, that we can write. What is the SI unit? See, what is the SI unit? SI unit of rho will be what? Charge means what? Coulomb. For the volume we will write per meter cube. Per meter cube, right? And the next, dimensional formula for the rho. Dimensional formula for the rho is what? Again, see, it's very simple. For the Q, for the charge, we will write A raised to 1, T raised to 1. And for the volume, we will write L raised to 3. So finally, M raised to 0, L raised to minus 3, A raised to 1 and T raised to 1. This is the dimensional formula for rho, right? So these are the three types of distribution in the textbook we are having. See, you just take the screenshot of this, right, and we will move ahead. Okay students, now moving ahead, we are going to find out what is the electric field due to the line charge distribution, what is the electric field due to the surface charge distribution, and what is the electric field due to the volume charge distribution. We will see it one by one, right? See, first of all, we will study the electric field due to the line charge distribution under the same heading, 1.13 continuous charge distribution. Okay. For that purpose, we will draw the diagram. First of all, see, line charge distribution, electric field electric field due to the line charge distribution. Right? See, we are going to draw the diagram. First of all, this is the XY coordinate system. X-axis, Y-axis with respect to origin. And in that origin, we will see a one line. See, this is a line, right? And on that line, we are having the uniform distribution of charges. Suppose the positive charges are uniformly distributed along the line, right? And due to this whole line, we are going to find out the electric field, suppose at point P. So our target is to find the electric field at point P due to the whole line. Initially, we will divide this line into small line segment. See, if we divide this line into small segments, and suppose consider one of the small segment. This is known as the line segment. Length of the line segment is suppose DL. We will consider one of the small line segment, and this line is at a position R. See, this is the R vector. So R vector is the position vector of the small line, right? And due to this, the distance of the line segment, the distance between the line segment and the point P is denoted by letter suppose R dash, right? So R dash is a distance of a point P from the line segment, right? Also we can say that this is a vector from line segment to P, and in the same we can say that that is a R dash cap is a unit vector in the direction of electric field, right? So we will write over R dash. See here, first of all, the line is divided into small segments. Consider one of the small segment, right? And position vector of the P point, that is denoted by letter suppose capital R vector. Here we will write what is R vector. So R vector is the position vector of line segment. Line element also we can write. Instead of segment, we will write element, line element, right? Position vector of line element with respect to origin, right? What is R vector, capital R vector? Position vector of point P, where we are going to find the electric field due to the line segment, right? So what is R dash? First of all, R dash is a distance of point P from the line element. Also we can draw the R dash vector, that is vector from element, line element to point P, right? And what is R dash cap? It is a unit vector. So this is the information regarding the diagram. Now see, here we are discussing about the line charge distribution. So for that purpose, see, here we are going to see that lambda is a line charge density, line charge density. Here we are going to consider that dl is the length of the line element. dl is the length of line element. Then dq are the charges remains present on the small segment, right? Total charges are suppose capital Q. Then we can say that small dq is the charges are present on the small line segment. So dq is the charge present on line element. Right? What we know that in the previous we studied line charge density lambda equal to charge per unit length. Suppose L is the length. Right? Over here, what is length? That is dl. So we will replace this capital L by dl. For the line segment we are discussing, length is dl. How many charges? So dq are the charges. Then what is the value of dq? Therefore dq equal to lambda into dl. The value of dq is what? Lambda into dl. See, okay, so we defined it over here, that is dq equal to lambda into dl, equation number 1. Now the electric field at point P, now electric field at point P due to small element will be, that is small electric field, that will be defined, that is dE vector. We are going to define it in a vector representation. What is the general formula for electric field? We know that E equal to what? K Q divided by R square. General formula. So K will be remains over here. What is Q? Q means what? Electric field due to the charges. Here the electric field due to the dq charges. So we will write, instead of Q we will write dq divided by distance square. What is the distance between the line charge and point P? That is, we have defined, that is r dash square, and that is r dash unit. If we are representing it by vector, so we have to write a unit vector over here. So this is the electric field. This is the electric field. dE vector is the electric field at point P due to the small segment. Due to this small segment, the electric field at point P is dE vector, right? Okay, but we are having number of vectors over here, number of vectors. So finding the total electric field, first of all we will simplify this equation. The Q remains as it is. Instead of dq we will write lambda into dl divided by r dash square into r dash cap. So this is a dE vector, right? Now for the total electric field, taking the help of summation. So electric field E vector equal to summation of K lambda into dl divided by r dash square into r dash cap. So this is our final equation. This equation represents the electric field at point P due to the whole line, right? In a similar way, we are going to find out the electric field due to the surface charge distribution in the next video, right? See, so you just take the screenshot of this. Board number 1, board number 2. Here your questions ends.